right, good morning, officially. So what I want to do is I want to move on to 2 samples for means questions. So what I did, I got kind of cheeky and I added some stuff to the notes from last day, then I posted them. So for example, I said I would finish the one example, but then I also included the confidence intervals. But I think at this point, you should feel pretty comfortable with confidence intervals. And so I'm just gonna kind of leave it with you to cover on your own. You just build a confidence interval. Potentially the hard part is interpreting the confidence interval, but for one sample mean, you're trying to capture the population mean, right? And so now I want to move on to talking about 2 samples, right? How do I compare 2 sample means? And there's actually 2 ways that we can do that. I'm trying to remember, I couldn't think of anything kind of administrative to do. So you've got the test that's going to open tomorrow. I've put off checking the timing, so I'll let you guys know exactly how many questions tomorrow, but aim for 20, but some of those are really short, right? So same as what I've said, but yeah, as soon as we put it off, I'm like, oh phew, I can put it off too, to check it. So anyways, I'll do that tonight. Okay, so let's see here. So I want to start 2 samples or 2 sample means. Okay, there are 2 ways that we can collect 2 samples. Okay, and maybe what I'll do is 2 samples. I'll switch the pluralness and you'll see why. 2 samples for mean questions. Okay, so if we're talking about the average of 2 groups, right, 2 samples, then there are 2 ways that we can collect that data. So I want to put this kind of in the middle at the top here. Okay, so there are 2 ways that we can collect and analyze 2 samples. Okay, the first one is if we have paired data. Okay, and so if we have paired data, then we've made 2 observations on one subject, okay, or arguably the same subject. Okay, so sometimes we stretch this paired data to be, a little bit more than just the one subject. I'll show you in a bit, but so paired data is when we have made, and I'll bump this over here maybe. So paired data is when we made 2 observations on one subject. Okay, what that translates to is you'll have 2 columns, right? And 2 columns means you have 2 samples, right? A sample can only go in one column, right? And so here, if it helps you to think about the 2 samples, it means that you have 2 columns of data in a spreadsheet. Two columns of data. Right, so what we're talking about is how these 2 columns are related or not related, right? And so if we have 2 observations on one subject, then our spreadsheet might look something like this. 1, 2, and then we've got maybe a pre-score and then an after score. Right? But each observation contributes to each column, right? So these are paired on this one observation. Okay? So here we might have something like, I don't know, 14 and then 62. And then this one maybe was at 54, 67. Who knows what these scores are, right? I'm just making them up. It could be anything, okay? But before and after situations, you know, before a treatment and after a treatment, okay? Test 1, test 2, maybe a test and then a final exam, right? So there has been something has happened in between there, and we suspect there's been a change, right, in the pre-scores and the after scores, and that's what we want to test. Okay, what we want to test is actually if the mean difference has changed or is different from 0, and there's a lot of difference in there, and so the context is really going to lead you here, and that can be really difficult, right? Is the mean difference different from 0? Ugh. Okay, and so what we do is for paired data, okay, we have this pre-score and then we have this after score. So for example, we could talk about test versus final exam, right? We could do before a medical treatment versus after, right? So some pre-post situations in general. Okay. So when each of these measurements, right, if they're in the same row and that means something, right, if that means that they are an observation on subject number 1, right, then you have paired data. Okay, so part of the problem is identifying when you have paired data, okay, because what happens is, and pretty cool, is that what we do is we say, okay, well, I can actually capture this movement in the pre and the post scores. Let's call them post scores. And just the word escaped me earlier, that's all. So pre-post, what we can do is we capture this difference by actually calculating the difference. Okay, so what we do here is we create a new column of the difference, which is the pre minus the post, or post minus the pre if you prefer, right? Usually there's some reasoning in how you do the subtraction, but for me, I always just read from left to right, because then I can just do 14 minus 62, 54 minus 67. So notice when we calculate this difference, it doesn't actually matter where you started from and where you ended up at, right? Now we're looking at, okay, how big was this difference, okay? Because what could happen is 14 is presumably a really low score. Now, the difference between 14 and 62, that's huge, right? Someone, you know, had a huge change over that amount of time. Now, going from 54 to 67, that's not so big, right? Because you started kind of high and then you went, you know, a little bit higher than this first observation, but not that much higher, right? So the difference here wasn't as large. So what we end up doing is we analyze the differences, okay? So what we would do, right, as long as we're consistent in the order that we do the subtraction, because otherwise you're going to flip-flop and then it won't make sense, right? So 14 minus 62 puts us at negative 48. 54 minus 67 puts me at negative 13. So in general, right, there was a difference of 48 and a difference of 13. Okay, and then we would keep going. Okay. So here, I'll say, where should I do? Order here, order doesn't matter, but must be consistent. Okay, and I think that's, you know, pretty reasonable. So what we do once we've absorbed all of this information, these two columns, we've melted them into one column. Now we're back to one sample mean, right? And what we're interested in is, we're always just interested in, is this mean difference different from 0, right? Because a difference of 0 means what? Means that you have, there's been no change, right? So for paired data, we analyze the differences I'm slowly kind of squeezing myself out of the other option, which is 2 independent samples. But I think just kind of keep that in mind, that I do want some room here, but it'll be more straightforward. And maybe what I'll do is try to keep it on the same page here. So for paired data, we analyze the differences, specifically comparing the mean difference to 0. Specifically comparing the mean difference, oh man, I'm going to start over there. Hey, that was a mess. The mean difference to 0, right? Note, a difference of 0 means that there's been no change, right? So if the difference is significantly different from 0, yikes, right? Then we have some change. Okay. Note, let's see here. If the difference is 0, there has been no change. Okay. So what we do, what's nice about, once you've identified paired data, then the null hypothesis is always the same. Okay. So the null hypothesis is going to be that mu, and what I like to do is I like to put a little mu diff or a little mu d, if you prefer, right? Just to indicate that, okay, this is the mean of the differences is equal to 0. Okay, and so this will always be the same. Always the H naught for paired data. So that's really nice. Once you have figured out that you have paired data, you also just know that that is your null hypothesis. Okay. The alternative hypothesis, the default, remember, is that it's not equal to 0, right? There is some significant difference from 0, right? But you could do less than 0, greater than 0, depending on the question. Can get a little bit tricky, right? Because the difference, it depends on how you calculated the difference. For example, here, these are all negatives. And so if we wanted to know if the post scores were higher than the pre-scores, then we would want to know, right? And that's the trend that we're seeing, right? Is that the post scores are higher than the pre-scores. So then we would want to analyze, is the mu diff less than 0, right? Because we're getting negatives here. And so is it significantly less than 0? Okay, so it depends on how you calculated the differences, right? Because if I had done post minus pre, then these values would be positive. Then I would want to check, is the mu diff greater than 0 for the same question? So it depends on how you calculated the difference. Okay, so the alternative hypothesis, mu diff does not equal 0. Okay, but this here depends on the question. And depends on how we calculated the difference. And depends on how we calculated the difference. Okay. So in terms of the null hypothesis, that's great. We always know what it is. As soon as you've identified paired data, then you're kind of off to the races, because you know how to treat a one sample mean problem, right? And so now so this would be our step 1, right? State the hypotheses. Step 2, I'll put it on a fresh page here, is do the test. So if we're back to a one sample mean problem, right, just looking at the mean difference instead of, some mean compared to some value, do the test. T is X bar of the differences minus mu diff divided by S diff over the root of N diff. Right, this is the same as before. Just everything is about the differences, right? The mean of the differences. So once you have that one column of differences, then you can calculate the mean. You can calculate the standard deviation. Right? You don't have to do that by hand, but you also have the number of the differences, right? So that can get confusing because the sample size is just the sample size of the differences. Sample size equals number of differences. Okay. What do we need for T? We need the degrees of freedom, and we just use the number of differences minus 1. So the degrees of freedom is N diff minus 1. Sorry, I've got a crazy runny nose today. Anyways, oh well. But once you have your T, right, which is exactly like a one sample t-test, okay, except now this value here is going to be equal to 0 always for paired data. Okay. So then once you have your T, you can use the t-test with N diff minus 1 degrees of freedom, and then all the rest of the steps remain the same, right? Remaining steps remain the same. Remaining steps, maybe I shouldn't use the same word twice. Remaining steps are the same. Are the same as always. Notice that I'm focusing on the hypothesis test, right? Because that's the hardest part. But of course, you can build a confidence interval, right? But just remember that you're talking about the mean difference, right? And so all our inference, let me see here if I've got a note for paired data. Our inference, right? So hypothesis testing or confidence intervals, our inference will be about the mean difference. Will be about the mean difference. Okay, so that's important. So if you go to your formula sheet or that one that I posted, right, then you've got all the formulas and it really has everything that you could possibly need in order to tackle this problem. So sometimes I'll call it matched pairs, and usually I like to call them matched pairs because it really emphasizes that things are being matched, right? There's some natural matching going on between the two samples, right? But here I have even included that it's talking about the mean difference. Okay. And so the null hypothesis, the alternative hypothesis, right? The sign can change, but the default is always not equal to. I've got the t that you calculate. I've got the degrees of freedom on here. And of course, we can build a confidence interval for the mean difference. Okay. And the t star that you find depends on the degrees of freedom. But besides that, there's really nothing crazy going on here. It's just the interpretation where you have to change your kind of change what you're saying, because now you're talking about the mean difference. And that's really important. Okay. So I want to talk about two sample means. Okay, two independent sample means. Okay, so here we had paired data. So the first thing we want to do is just identify, okay, what type of question do I have? Do I have one sample or do I have two samples? If I have one sample, it could be about the differences, right? It could be one sample of differences, which means you have paired data. Right. And that's kind of a dead giveaway that you have a matched pairs or a paired situation, right? If I give you the mean of the differences, then you know you should be using paired data, right? Whereas the other option, let me go way back up here. Whoa. The other option is if we have two independent samples. So if we have two independent samples. Okay, so there's no way to naturally, oh, internet troubles. Yeah, it happens. Very annoying though for you, not for me. So let's see here. Two independent samples. Okay, so yeah. So if we have no natural way of matching these samples, then that's fine. Then we just have two independent samples, right? If we think about, okay, students at the college versus students at UBCO, for example, there's no way to say that this person should be matched to this person. And that's okay. We don't need that, right? That's what we would need if we wanted to do a paired samples t-test. But if we just want to compare the means of two groups, then we would use a two sample t-test, right? In general, we're using t-tests. And honestly, for anything that you do in work situations, it's usually going to be a t-test. So, and I'll take it even one step further. It's usually going to be a two independent samples t-test, right? You're comparing the mean of group one to the mean of group two. Okay. So no natural pairing between the two columns of data. Or I'll say samples first because they are samples, but then I'll say columns of data. Because I find that helpful, right? And so if my data set looked something like this, and maybe I have, you know, OC and I have UBCO, then I might have, you know, two independent samples. Okay. What's nice is those two samples don't even have to have the same sample size. Do not even need anyways, fine. Do not even need to be the same sample size. Oops. The same sample size. And that's pretty cool, I think. We can have different sample sizes for the two groups. The only thing that's tricky, and we've seen this before with proportions, right? As soon as we move to two sample proportions, we wanted to compare the two, right? So now I'm going to have a mean for group one, a standard deviation for group one, and a sample size for group one. And then I'm going to have the same information for group two. So my formula gets a little bit bigger because I need to incorporate all that information. But beyond that, there's nothing really going on here. Okay. And so with two samples, two independent samples, we have information from both samples. We have information from both samples. So group one is going to have some X1 bar, S1, N1, right? And group two is also going to have some mean, some standard deviation, and some sample size, and they don't even have to be the same. So group two is going to have some X2 bar, S2, N2. Okay. What we want to do for, just to kind of match things up here, so I talk about the same stuff. What we want to do is we want to analyze the difference in the means, right? How does the mean of group one compare to the mean of group two? So just like in proportions, we can talk about does mu1 equal mu2, or same thing would be, is mu1 minus mu2 equal to 0, right? You can see how both of those mean the same thing, right? So for independent samples, for two independent samples, we analyze the difference in the means. Oops. The difference in the means. Okay. So our null hypothesis, right? It can take two forms, and it's really just a matter of what you like. I like to look at mu1 equals mu2 because I find that it's a little bit easier to wrap my head around if I want to compare, for example, mu1 is less than mu2. Otherwise, you'd have to think about, okay, what does that mean in terms of the difference compared to 0? So for me, I like to just have mu1 equals mu2, but I'll show you both ways. So the null hypothesis, let me see here. We'll put it on a fresh page. So step one is to state the hypotheses. And my null hypothesis is going to be, I'll use mu1 equals mu2. As always, right, we always have to talk about the population mean, right? Whether that be the population mean difference or the population mean of group 1, group 2, right? We're always talking about mu for means questions, and we're always talking about P, the population proportion, for proportion questions. Okay. Or you could use mu1 minus mu2 is equal to 0. Okay, so these are the same, and you just need to pick which one you like, and then just stick with that. Okay, I prefer this one. I just think it looks a little bit nicer, but imagine, okay, so you've got mu1 minus mu2. What if you add mu2 to both sides? Then you have mu1 equal to mu2. And I mean, logically, if you subtract two things that are the same, then you get 0. Right? So they're the same. And the alternative hypothesis is that mu1 is not equal to mu2, but this depends on the question. Depends on the question. Okay. And then, so of course you could have mu1 minus mu2 is not equal to 0, or is less than 0, or is greater than 0. But again, that would all depend on the question. Right. Or HA mu1 minus mu2 is not equal to 0. And I'll circle that and say that that depends on the question as well, right? So if you've taken this approach and you want to show that mu1 is significantly less than mu2, what would that mean in relation to 0? Well, it would mean that I would get, so if mu1 is smaller than mu2, then these values would always be negative, right? Which means that mu1 minus mu2 would be less than 0. Right, so there's a lot more thought going into that. Whereas here, if I wanted to show that mu1 is less than mu2, I can just put that in there, right? Or you could rework the equation. Doesn't matter as long as you remember your inequalities. Okay. So let's see here. So for doing the test, we've got a little bit more work ahead of us. Okay, and so not bad. But it's just because we have all this extra information now, right? We have information from either of the groups or from both of the groups. So let's see here if I want to add anything before I go on here. I think covered all my bases. Okay, so what's nice is that our estimate is going to be x1 minus x1 bar minus x2 bar. Okay, so our point estimate for mu1 minus mu2 is x1 bar minus x2 bar. That's our best guess at what mu1 minus mu2 is. Right, because again, right, remember, we're analyzing the difference in the means, right? Mu1 minus mu2. And maybe I'll do this. Mu1 minus mu2, right? If they're the same, then that difference is not significantly different from 0. Ugh, okay? Gotta just stay on top of all the words. Okay, so let's see here. So the point estimate is x1 bar minus x2 bar. Now I'm going to tell you what the standard error for that point estimate is. So the standard error for x1 bar minus x2 bar is, okay, it's going to be the square root, I've got this, of s1 squared over n1 plus s2 squared over n2. I'm going to confirm it, but I'm going to write it down. Because I'm feeling pretty good. Okay. What's nice is that's the standard error for the confidence interval as well as the hypothesis test. So unlike for proportions, right, we had different standard errors depending on if we were doing a confidence interval or a hypothesis test, whereas for a means question, it always stays the same. So that's really nice. Okay. Now, so we can do the test, right? Step 2. So we use these. We use these in step 2. Do the test. So T is going to be x1 bar minus x2 bar. Technically, right, because we take our point estimate, right, minus the null value. Okay, so here I want to highlight that this is our point estimate. So the setup stays the same. It's just that our point estimate and our null values are now bigger, right? Minus mu1 minus mu2. But this is always 0. Null value equals 0 always in this case. Okay. Divided by the standard error, which is that s1 squared over n1 plus s2 squared over n2. Okay. So this is the standard error of the point estimate. Right, so as long as we have those building blocks, it doesn't really matter how large our point estimate and our null values and our standard errors get, we can still handle that, okay? And now that we have 2 sample sizes, how we find our degrees of freedom, there's a huge calculation that we could do and that R would do if we asked, some sort of software to run our calculation for us. Then it does a fancier calculation, okay? But for calculations by hand, what we use for our degrees of freedom is the smallest sample size minus 1, okay? And that's our most conservative estimate. We're not trying to max out our degrees of freedom, it's fine. And so the degrees of freedom is the minimum of n1 minus 1 or n2 minus 1. This is just the smallest sample size minus 1. Okay. So you find your smallest sample size minus 1. Technically what you're doing, right, is this minimum function on n1 minus 1 and n2 minus 1, but really the minimum of these two will be the smaller of the sample sizes minus 1, right? So you can just think of it as the smallest sample size minus 1. Okay. I will have a little asterisk here. Okay. This degrees of freedom calculation is a conservative estimate that we use for hand calculations. Software will have a more precise degrees of freedom. So using software, would yield a more precise degrees of freedom. Okay, and it's a huge formula. I'm gonna just scan the notes that I have. I'm kind of following loosely. I mean, I've talked about this so many times, but I can't remember if I have. Oh yeah, too funny. Let's see here. There's some examples in here, but oh yeah. So technically, the degrees of freedom would be this, but we don't want to do that, and we don't need to do that, right? I would prefer to just use the smallest sample size -1, right? That's nasty, right? Would yield a more precise degrees of freedom. Specifically, it would use this, right? But we're going to use this degrees of freedom. Okay, so that's good. Okay, so if we pull in, we've got our test and we've got our standard errors, and then for independent samples, so for 2 independent samples, then our analyses will be about the difference in the means. Okay, so here, once we have a t, I'll just finish this here. So once we have found the t and the degrees of freedom, the remaining steps are the same as always. Okay, so that's good, right? Once you have a t, you can take that calculated t and try to place it along your degrees of freedom line, and then you're able to find the p-value. Once you have the p-value, if it's less than 0.05 or whatever alpha level I give you, then you have enough evidence to reject H0. And that's all the same as when we first started talking about p-values and stuff like that. And I know that it's tricky, it's very difficult in the beginning, but you're going to need to practice these problems, and then you'll start to see, okay, well, yeah, it is just the same. It's just a matter of setting up the null and alternative hypotheses, knowing what tests to run, right? And, you know, if you need degrees of freedom, what are they? And then you're kind of off to the races, right? So note, I want to have the same format of this for, yeah, okay. For 2 independent samples, our inference, hypothesis testing, and confidence intervals will be about the difference in the means. Okay. So I'll bring in the chunk from the formula sheet. Where is it? Here. Oh. So here, right, I've highlighted that this is the difference of 2 means, right, or a difference in the means, because I have 2 independent samples, right? We can talk about it a couple of different ways, but right here, our hypothesis is going to be how mu1 minus mu2 relate to 0, right, or what they are. And so here I've used this setup, but you could talk about mu1 minus mu2, how it compares to 0, that's fine. But either way, your t is going to be, and good, I had my standard errors all nailed down. Okay, good. So you want to make sure that when you're doing these calculations, you don't want to forget about the square on the standard deviation, okay, on both of them. So let's see here. So here it's always going to be minus 0, right? Because mu1 minus mu2 is always 0 in your null hypothesis. Okay, and so what's nice is this will always be your null and alternative hypothesis. Save this sign here, that might be different. Okay, so you can find the confidence interval just as well, right? As long as you know how to find your degrees of freedom, which is also on here, the smallest of n1 minus 1 or n2 minus 1, then you can find your t star for whatever confidence interval you want to build. Okay, so the formula is more complicated, but the steps all stay the same, right? You just need to be really careful with your order of operations here. For example, right, you want to do s1 squared, divide that by n1, put it to the side, s2 squared, divide it by n2, and then add that to whatever you found previously, and then don't forget to take the square root, right? Because then otherwise your t is going to be huge. Okay. Or tiny, I guess. Good. So I've got a couple of questions in the notes with solutions in there. So what I want to do is I just want to read the questions, because what I find is the hardest part is reading a question and then figuring out if it's a paired sample or if it's an independent sample situation. Okay, so I'll go grab some of these questions. I mean, they're broken up, but let's pretend they're not. So if we read this question here, and maybe I'll just use part A. Okay. 200 observations were randomly sampled from a survey called High School and Beyond. The same students, okay, took a reading and writing test, and their scores are shown here, not here, but in the notes. Okay. Are the reading and writing scores of each student independent of each other? Is this paired data, right? And so here, as soon as we see the same students took a reading and a writing test, right? So now if you imagine your data set, right, you imagine your spreadsheet, you would have student 1, student 2, student 3, and then you would have their reading score and their writing score. Okay, so then we have paired data, right? So here, this is paired data. Because it's paired on each student. Once you've decided that, right, what's your null hypothesis? Well, it's that mu diff equals 0, and your alternative hypothesis, it would come from a later part. Let me just see here, crop. Appear to be a difference. So this means that the null hypothesis is that mu diff equals 0, And if I want a difference, then what I'm testing is that the alternative hypothesis is that, whoops, mu diff does not equal 0. Okay. So if there's a difference, then we don't care if it's less than 0 or greater than 0. We just want to know, is it significantly different from 0? The mean difference. And then I feel like you should be able to kind of take it from here, right? So let's read the remainder of the questions. And let me see here. Oh, haha. Are the assumptions for inference satisfied? So for a t-test, right? In general, for a t-test, we said there are 2 assumptions. In general, and maybe I'll say, just to emphasize that we have talked about this before, recall, in general, a t-test requires 2 conditions, or a t-test. And as soon as we calculate a t, we're running a t-test. And so there's 1 sample t-test, there's 2 sample t-tests, but in general, and you'll hear that a lot when you are kind of out in the real world. If anyone is ever doing any stats, it's a t-test. I can almost guarantee you that. Okay, so so it helps to know the lingo, right? Because, okay, I'm going to run a t-test. Oh, can't you just run a t-test? Oh yeah, people love saying that. Right? Oh, just run a t-test. Oh, I just ran a t-test, whatever. And so what they're doing is they're analyzing 1 or 2 means, okay? We're just comparing them. And typically it's a 2 sample t-test that they are talking about. So in general, a t-test has 2 conditions. Okay, independence, which came from the sample or samples were randomly selected. Sample were randomly selected. Now, in the case of paired data, right, of course, we're saying that they're paired on the subject, right? But what we're assuming and what we have to check is that each subject, so each student in this case, was randomly selected. Okay, and so let's see here. 200 observations were randomly sampled from a survey called High School and Beyond. And so here it looks like it was satisfied, right? And so as long as your sample of subjects were randomly selected, then it checks out, right? Whereas for 2 independent samples, then you would have to say, okay, sample 1 was randomly selected and sample 2 was randomly selected. Either way, you're checking, were the samples randomly selected? So independent samples were randomly selected. So for paired data, then the subjects were randomly selected. And for 2 independent samples, each sample was randomly selected. Each sample was randomly selected. Okay. And then we have the normality condition. Okay, so the normality condition for means is really nice because as soon as we have a sample size that's larger than 30, we can assume normality because of the central limit theorem, which says that, okay, even if you're pulling from a slightly skewed distribution, the means will start to follow a normal distribution as soon as we hit kind of 30, a sample size of 30. If the sample size is less than 30, then you would need to make a histogram of it, potentially, and just kind of look and argue that they follow a normal distribution. Okay, so either the observations have to be approximately normal. Okay, so if n is greater than or equal to if n is greater than or equal to 30, the central limit theorem applies. The CLT, remember the central limit theorem, applies. And we may assume normality. Okay, but if n is less than 30, oh, and I wanted to show so n greater than or equal to 30, but I wanted to say it. Hilariously, I was, on Facebook Marketplace the other day, and someone was, they wanted it to be less than something, but they had used the wrong sign. So thought about messaging them and saying, your inequality is wrong, but I didn't do that. Hopefully they figured it out. I think the context everyone understood. But anyways, so inequalities can be hard, but so that's why I wanted to write it out. But if n is less than 30, we have to check the distribution, and if the distribution looks approximately normal, then it's satisfied. The distribution of the sample must be approximately normal. Or we must assume it's approximately normal, right? Either way, we have to argue that it's approximately normal. Or we must assume it is approximately normal. Okay, so those are the conditions. And of course, here, the normality condition is on the differences for paired data, and because those are the observations that we're using in our calculations, and for two independent samples, then we need each of them to follow a normal distribution or approximately a normal distribution, or if the sample sizes are more than 30, then we're good to go. Okay, so for paired data, maybe I'll say paired data, the differences must be approximately normal, or if n is greater than or equal to 30, we can assume normality. For independent samples, and I'll say two independent samples, then either the sample sizes must be larger than 30 each, or approximately normal. So each sample must either be larger than 30 or follow an approximately normal distribution. Follow an approximately normal distribution. Okay. Good. So those are the conditions, and honestly, they haven't changed from the one sample case, and they're relatively easy, right? We just have to make sure we have a random sample and that we can assume that we have a normal distribution. And once we've kind of checked those boxes, then we move on and we can apply a t-test, and a t-test is relatively robust. Right? It can handle non-normality. It can handle a little bit of dependence in your observations. It can handle all that, right? And so we just need to argue that it's reasonable to go ahead with the t-test. Okay, so the assumptions here are a little bit more relaxed than for the proportions. So that's nice because we can kind of get into the t-test right away. Okay, so here we already set up, so do these data provide convincing evidence of a difference between the scores on the two exams? If we have the mean and the standard deviation of the differences, we can do the t-test and we can find the p-value. And so this would be a full-blown hypothesis test. So do the hypothesis test. Right. And the answers are in the notes that I posted. So that's why I'm just reading these so we can figure out what we need to do or what we would need to do. And then I want to do another example as well. So if we were to construct a 95% confidence interval for the average difference, right? So for mu diff between the reading and writing scores, would you expect this interval to include 0? So that's going to link back to the hypothesis test. Did you reject H naught? Okay. If you rejected H naught, then you would not expect this interval to include 0. Okay. If H naught was rejected, we would not expect the interval to include 0. Right? Because if the interval includes 0, then we shouldn't be rejecting the null hypothesis, because then we're 95% confident that 0 is one of the options, right? And so if H naught was rejected, I'd hate to know how many spelling mistakes or typos, let's call them, I have in my notes. Who knows? If H naught was rejected, we would not expect the interval to include 0, right? So you can build the interval to confirm the interval. So a confidence interval only matches a two-sided test. Okay, so if you're doing a one-sided test, it might not necessarily match. Okay. Okay. Where are those? Here. So here, the data, if you want to play around with the data, it's actually stored in the open intro package. So you would have to install the package called open intro and then call the library open intro. But this data is actually stored in HSB2. Okay, and so we can do things like, and I've shown you the code for doing all these things, the kind of basic things. And so we can make a box plot, right? And so we can look at the box plot, and remember, a box plot that's relatively even around the mean follows a normal distribution, right? And so here, although there's a little bit more squish here on top than there is on the bottom, I would argue that it's approximately normal. Both of the scores are approximately normal, for example. Okay. And so we can calculate the differences. I did read minus write, and I can store them as the differences. Then I can look at the histogram of the differences, and it definitely looks like, oh, you want to use ggplot, do you? No, ggplot is awesome. But I will say, yeah, I will say I wouldn't waste my time with ggplot unless you feel really, really comfortable with ggplot. For this quick kind of things that are not going to be included in your report, I wouldn't bother with ggplot. The base plots, they look bad, right? This is not a beautiful histogram by any means. You can make a beautiful histogram in ggplot, right? But we're just seeing what's going on here. This isn't going into our report. But I mean, if you want to, you can use ggplot. You can tame ggplot. I mean, once you kind of get the hang of the layers, it's fine. But yeah, so let's see here. So now we have the differences, right? And so I've calculated the differences here, and I've stored them in a new column that I'm calling diff. Okay. Now, I could, if I wanted to, still do this by hand, right? You don't want to have to calculate the mean and the standard deviation of 200 differences. That sounds insane, right? And so you can use the mean of the differences and the standard deviation of the differences. One thing that I will note is, depending on how comfortable with R you are, right? Especially if you are in the data science track, then you'll know that, we shouldn't use the $ reference every time because it's clunky. But I do find that it's the easiest way when we're just getting started, right? So some people are coming from biology because it's cross-listed. And so then it's easier if you can just see, okay, go to the HSV2 data set. That's the name of the data set. And then $diff tells it to pull out just the diff column, right? And then find the mean of that column. Same thing with the SD, find the standard deviation of this column, okay? I can use those values. I can use those to calculate the test statistic or the t-test, okay? Or I can just use R to do the t-test for me. But so here, and there's a typo here, but oh well. We could use the t-table, right? So I've shown you, and remember, in the boxes is all the work that you would need to show, right, for a written answer. So here, right, we'd have to find our degrees of freedom. We can find the value that our t falls between on our t-table. So you're gonna have to play along with these instructions. It doesn't help to just read these and say, oh, okay, I get it, right? You have to look at the t-table, find your 100 degrees of freedom line, find and convince yourself that this all makes sense. And then why do we want a two-sided p-value? Well, because I want to know if it's different from 0, right? So my p-value is somewhere between 0.3 and 0.4. That's large, right? And so we can draw our conclusion, right? And then I've got the answer to that confidence interval, right? We do expect it to contain 0 because our t-test was so small, right? Or the t.test command. We've seen it before, right? We gave it some column and then a null value, but now what we're saying is here's column 1 and here's column 2, and then I'm going to tell it paired is true, okay? So then it knows to go through and find the differences. It finds the mean of the differences. It finds the standard deviation of the differences. It calculates your t with the proper degrees of freedom. So here it is using 199. We can't do that because our table doesn't have a 199 line, right? But it gives us the p-value of 0.3868. Now, just convince yourself, right, that 0.3868 is somewhere between 0.3 and 0.4. So this interval is not bad for the p-value. It still gets the job done. But if you want something more precise, then you're going to need to use software. Okay, so the alternative hypothesis, the default is if you want to have a two-sided test, right, then it'll give you the confidence interval as well for the mean difference. Okay. So the mean of the differences is negative 0.545. So this t.test command has pretty much everything that you would need. Right. Okay, let's see here. Oh, I was there. So I love Jocko's Garage, the Jocko's Garage example, but I just want to read the example, and then you can work through the mean and the standard deviations, and you can work through the problem. Don't worry, I actually give you the mean of the differences and the standard deviation of the differences. One thing that throws people off is when you have the differences here, the difference in the means is going to be the mean difference, okay? That's not true for the standard deviation because it's looking at the standard deviation of the differences. So you don't want to just calculate across. Right here, I've got, if you're working through these, I don't want you to have to find the mean and the standard deviation, although it might be nice, right? And so they're in there if you don't want to do it, but it might be nice practice. So the situation is insurance adjusters are concerned about the high estimates they are receiving from Jocko's Garage. To see if the estimates are unreasonably high, each of 10 damaged cars was taken to Jocko's and to a trusted garage. So now we're making two observations on one car. Right, Jocko's Garage and a trusted garage, and estimates were recorded. Is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? And let me just confirm here in the solutions, because I feel like okay, no, I fixed it. It used to be it used to go against itself and ask if there was a difference in the quotes, which makes it an easier question, right? But here, significantly higher, right? That's going to get factored into your alternative hypothesis, right? And it depends on how you calculated the differences, because this is paired data, right? Paired, because we have two observations on each car, right? So if we want to look at the difference between Jocko's estimates and the trusted garage, we would have to calculate that difference, and then we analyze those differences. Okay. What I'll do is I'll add the solutions, because it doesn't look like the solutions are in the notes. So I'll add that in here. Because I have them somewhere. I will add the solutions to this one. At the end of the notes, at the end of these notes. Okay, because I don't think they're in there. Same thing for example 7, it is paired data. So I want to look at 2 independent samples question, right? But the solutions are all in here. And same thing for the wetsuit versus no wetsuit question. So you have swimmers and they're going to be using a wetsuit or not using a wetsuit, and we're checking their times, I think, in swimming. Same thing for this one. I'll add the solutions for this one as well. Oh, Okay. So this one has the solutions in it, but I want to talk about why it is 2 independent samples. Whoops. So kind of a fun question. It makes you think a little bit. So the weights of diamonds are measured in carats. Okay, so the difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the naked human eye, right? And so, but does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? Now, right away, we start to suspect that it's 2 independent samples, because a 0.99 carat diamond is a 0.99 carat diamond. There's no way for it to be a 1 carat diamond as well, right? And so the observations here are going to be independent, right? You collect 2 random samples of diamonds, right? And so here, 2 independent samples. Okay, and there is some conversion here, just so we don't have to talk about these tiny decimal places. We've converted to a point difference. So that's kind of a sneaky trick that we can use sometimes. But really it doesn't, it doesn't matter. 1 carat diamond is worth 100 points, we're calling it, and a 0.99 carat diamond is worth 99 points. Okay, and so that just makes it a little bit easier to think about, because then we're talking about the point price. Okay, so if 1 carat diamond has 100 points, then the average point price is 53.43, but there's 100 points. And so each 1 carat diamond, 53.43 times 100 is on average 5,343. Okay, versus on average, right, each point in a 0.99 carat diamond is it costs 44.50, right? But there's 99 of them, so you'd have to multiply by 99 to get the cost per that diamond, right? The average cost. But our question asks, is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? So we are just analyzing these differences. So we don't need to convert them back to per diamond prices. And that was the whole goal, right? And so here you've got your X1 bar, X2 bar, S1, S2, N1, N2, as long as you're consistent with group 1 and group 2, right, we should use question specific subscripts. In the null and alternative hypotheses. Oops. Okay, so for example, so that is H naught would be mu1 is equal to mu 0.99, right? Versus the alternative hypothesis that mu1, we want to know, is there evidence that the average point price of 1 carat diamonds is higher? So then mu1 is greater than mu 0.99. You can go back to just 1, 2, because it gets really messy for your t-test. As long as you've established your groups, right? Or you're using question specific subscripts. So that's the same as when we had two sample proportions, right? And so it's just for the reader to know what you're talking about, right? Where did this number come from? And I see that I'm plumb out of time, way over time, way over time. Let me just scroll down here. Of course, the solutions are here. And what I'll do is I'll post the remaining solutions. There's a kind of a fun social experiment here, colored red. So I'll post those solutions and you'll have to go through them and practice them on your own. And I've also posted the assignments, right, for you to work through. All right. I'm all out of time. If you have any questions, let me know. Otherwise, I'll see you tomorrow morning.